right, well, thank you for joining us for this last workshop of the day. And I'd like to welcome Dr. John May, a distinguished colleague and a fellow math group member and a software architect here at Maplesoft. And John will show off some interesting Maple language features as he develops solutions to advent of code challenges. So welcome, John.
Thank you for that only slightly flattering introduction, Kashka. Um, so I'm going to talk about one of my hobbies, which turns into work because why wouldn't it? Which is solving advent of code. These are coding puzzles. Um, and I do them in Maple, and I'll talk about what advent of code is. I'll talk about what Maple is. Hopefully everyone knows that. And then we'll just do some of these. This is meant to be a kind of fun workshop. Uh, I'm going to talk about uh, sort of cool things in Maple that make it easy to solve this sort of code challenge and some pitfalls and some benefits to, combining your hobbies and your work. So, all right, looking through. Okay, so what is Advent of Code to begin with? So, Advent of Code is it's like an Advent calendar. So it's a Christmas themed uh, code puzzle. So there's 25 doors in an Advent calendar for Christmas, and you open them on the first day of Christmas and you eat chocolate but instead of chocolate and instead of a calendar, it's a web page. And instead of chocolate, it's programming challenges. And so this is run by Eric Watzel. He's been running it since 2015. Um, it started as kind of a low-key thing he created for his friends, a bunch of code puzzles, and then it's blown up. And now somewhere in the neighborhood of 200,000 people uh, solve at least one advent of code uh, puzzle every year. So there's a lot of people participate. This year will be the 11th year. I've done it for 4 years before now. So, and you can see here, this is taken from the web page. It's an advent calendar of small programming puzzles for various skill levels that can be solved in any programming language. And people do it for all different reasons. So the calendar puzzles open at midnight at Eastern time, and people uh, people often get the puzzles right as they're released and see who can do them the fastest. And if you know anything about competitive programming, you know that the fastest people are inhumanly fast, and you can't really compete with them unless you sometimes the puzzle is something that you know exactly how to do and you don't make any errors, and you can sometimes get into the top 100 if you're lucky. But nowadays, there's enough people cheating with AI code generators that the the leaderboard's no longer fun, and actually there will not be a global leaderboard like that going forward after this year. But let's talk a little bit about these puzzles. All right. And all right, so I think I covered all the most of this. So 25 days, there's a new puzzle released at midnight every day. Um, they so it's not presented in a computer science fashion. Instead, it's a story about you, the programmer, helping elves save Christmas. And so it's convoluted. So there's a reading comprehension issue, in addition to actually solving a programming puzzle. Um, so then there's a sample input given to you in your problem, but then every individual user gets their own input so that everyone is going to have a different answer. The the solution to the problem is always going to be a short string that you enter into the website. Um, and so that means you can solve it however you want. You can solve it on pen and paper. You can solve it in, God forbid, Rust, or Maple if you're a right-thinking person. Um, and then you get the answer, you just paste it into the web page. Um, and then after you've solved the first part, you'll get a second piece of the puzzle to solve again. So every day there's sort of two parts to the same puzzle using the same input. So day one usually starts easy, and then by somewhere in the middle, usually day 17 to 21 are incredibly difficult, and then day 25 is usually a gimme. So it's always a journey every year. So I am fortunate. The puzzles actually drop at 9 p.m. at night on the west coast of the US. So I can put my children to bed and then work on the puzzles. So all right. So let's just so the question, why do I use Maple to do it? And I mean, the reason is that I program in Maple every day, all the time. And so it is extremely comfortable to write in Maple. But also for this sort of puzzle, when you have an input that's in text and you're trying to turn it into a program, things you can manipulate programmatically, the worksheet interface is actually extremely nice for putting data in, trying commands, iterating on those commands, building small programs and iterating on them. So I actually solve these problems completely inside the worksheet interface. Um, Maple is great for this because it's has all of for a 30-year-old language, it has like all of the modern data structures that you need to do high level math. And it took until the last 5 years for other high level languages to actually get all these things like sets and hash tables and everything at the top level. But Maple has all those things, and it makes it very easy to do lots of stuff. Um, I And in fact, the fact that Maple, oops, I went back. How do I go back? There we go. Occasionally you get a problem where you instantly recognize it as a problem from number theory, and then you're like, ah, Maple has a command for that. And then you can solve a difficult part of a problem very easily. Um, and then actually I do this partly to discover bugs and stress test Maple, um, because I mean, because occasionally this solving code puzzles will like force me to solve sorts of problems I don't necessarily get from bug reports and or problems when I'm tinkering on algorithms deep in Maple. So it forces me to work on different sorts of things and see how well Maple works for those things. So it's a it these problems are fun, but it also gives me a way to sort of use Maple in ways that that I don't necessarily do all the time, so that I can discover places where it needs to be fixed or places where we can make it better. All right, and then over here on the side, I will talk, actually we'll go do this problem in a little bit, is kind of what my scratch work looks like when I'm doing one of these. All right, but I figured let's actually just go do an event of code problem that I haven't done before. So this is, so I started doing these in 2021. So let's go to 2020, day one. All right, so you can see kind of what these look like. It's the screen is the right colors for people who uh, grew up in the 80s. And you can see we have a story here. It says that you've been saving Christmas for 5 years in a row, so maybe you won't have to this year. It's kind of a funny story. This introduces you to the whole shtick. Every day you solve puzzles to earn stars. Um, every day you earn 2 stars. You have to earn 50 stars by December 25th to save Christmas. Um, so, oops, let's see, where are we? So you're leaving and they want you to fix your expense report. So apparently something isn't quite right. So then they have your expense report, which is going to be your input, is a list of numbers, and you have to find 2 entries that sum together to 2020. So let's take the sample input and let's do this in Maple. So I normally start sample input. Let's go over to Maple. So this is my template for starting an advent of code problem. Um, Maple does this to me. This is a very helpful thing that Maple does, which is if you try to paste in a list of numbers, it turns them into a matrix, which is great a lot of the time. It's just not great right now when I'm doing it here. We're doing this live. So actually, um, if you have Maple on your desk, um, you can do this too, and you'll probably do it faster than me. So let's see. Okay, now we have this input. And the best thing in the world, oops, yeah, we forgot to run our widths, is string tools. String tools really like, whoops, I haven't downloaded my full input yet. All right, so string tools really is a champ here. And I don't need it does a lot of work for us. So I'm going to trim the input. So trim removes any white space. So uh, all these files end with a carriage return. So I trim them to get rid of white space in the beginning and the end, and then I split them. Here I'm going to split on a new line, and then I'm going to map my little helper function s2i string to integer. And so now, all right, okay, finally I have a list of uh, of numbers. So this is a day one problem. It's supposed to be very easy. So so we're trying to find the 2 entries of the list that add to 2020. So um, uh, let's just, let's go, let's be an I. Let's just walk through, do the n squared thing. And usually the n squared thing is good. So I'm going to check if split input. I should have used a shorter thing. I plus the input j equals 2020. It's going to break, do a bunch of ends. So I don't, when I'm writing my own code for good reasons, I usually do, well, none of those equal 2020.
Need to break the outer loop too.
Do I need to break? Oh yeah, break 2. Thank you. Oops. Does it just break? No, it's not a index here. It's break 2. There we go. And then, thank you, Alan. All right. Okay. So then we got split input 1, or I Split input J. All right, so that's equal to 2020. Okay, good. So now it's never just like positions in the list that is our puzzle answer. So here we take the two entries that sum to 2020, we multiply them together. So our answer here is going to be something like 500,000. So actually I wanted to take those. Oops. All right, I lost my. Let's multiply them. Okay, and then that's going to be our answer. So it's 1. All right, okay, but that's not our input. Our input is always bigger. So let's get our puzzle input. So you can see our actual puzzle input is a lot bigger. So let's save this. We're going to save it in our advent of code inputs. I want to call it AOC 2020. Let's see what I want to call it. 01 input. Okay. Oop, where am I? Where am I? Over here. Okay. 01. This is a little too verbose, but TXT. All right. Okay, so we save that. Now this should work. Oh.
It
So
says
some
2022 instead of 2020 on that
Oh,
line.
thank you. Also, sometimes when I go to Firefox, it doesn't give the script keyboard back to Maple. So, all right. So now let's read our input in. You can see it's a slightly bigger list. It's not really that much bigger. And so our n squared thing is fine. We're going to take our answer, copy it, go back to admin of code. We're going to submit our answer. And we got, that's the right answer. So we get 1 gold star, and then we get our part 2. So the part 2 is always on the same input. And so the elves are thankful for your help. And then they ask you to do something else. So they want 3 numbers that meet the same criteria. So now we're asked to find 3 numbers that add together to 2020. So fortunately, this is actually, in the grand scheme of things, a very, very tiny list. So we can just take our old answer and here. And we can just take our old answer and add another loop. And so we'll just do that. And so here you can see kind of, this is how easy these problems start. So sometimes the day 1 problem is a little trickier than this. But not always. The idea is that Eric Watzel wanted to create something that's approachable so that people can learn new programming languages and so it should be easy to translate from the word problem into a practical programming problem that people can solve in the first couple days. So let's actually I should actually check that my IJK good numbers. Yeah, okay. All right. So then, and you can imagine doing this problem at midnight in December and racing to do it as fast as you can before the speed coder Pythonistas can do it before you. So this is maybe not a super interesting problem. It's day 1 problem, but if you're trying to do it as fast as you can and you're trying to do it in less than 5 minutes, or actually less than a minute. It probably people are solving it in 90 seconds. In some cases, even without LLMs. And so, all right, so and then we solved the problem. It was as straightforward as it looked. After you've solved the problem, you should of course brag on your social media, and then you can see that I have gotten 1 star on the 2020 problem board, and there's 25 more to go. So we're not going to solve those all today, but you can see that you have leaderboards is like a global leaderboard that shows everyone. You can see that it times you from when the problem was released till when you solved it. So here, I was actually rank 200,011 on solving that first part. It's maybe a little more interesting if you look at so here's last year. So here, last year you can see that on day 1 I took 10 minutes to solve the problem, and that was good enough for to be in 4,000th place. And I don't think I got the closest I got to the top 100 was 280th place. So it's competitive, and so the problem has to be very oops. Yeah, so you're like day 1, you can see, okay, well, these are the LLMs, someone solving it in 9 seconds, but then these like 1-minute solves are genuinely problems that are actually genuinely speed coders. So, all right. Okay, so let's go back to the presentation. All right. So from here on, so this is like, that was an easy problem. I'm going to show you some harder problems that I've solved in the past there with solutions. But one reason it ends up being fun is it ends up, these problems end up going into graph theory and all sorts of areas of computer science. And I'll occasionally solve a problem and I'm like, there should have been a Maple command to do that thing I just did. Because I will go over to the forums where people are talking about how they solve problems, and they'll say, oh, I just opened Python and used networkx to do this command, and y'all look like, I should have had that in Python. And so, or I should have had that in Maple. So that graph theory got some new commands, I think last year. I wrote the minimum cut command just based on shouldn't click on things, on a rewritten version of the max flow command. And I did that in response to an advent of code problem. I actually solved that advent of code problem very quickly, but how it turned out that you formulated a graph and then you're trying to figure out what to do with that graph. So you plugged it into drawgraph, and drawgraph used a string-based or a spring-based visualization. And it turned out, even though there were thousands of nodes, you could see the 3 edges that had to be cut for the minimum cut. So you could actually just like look at the graph and read off the solution. But it's always very unsatisfying to solve something visually where you manually find the solution. And the non-visual solution was this min-cut algorithm. So now Maple has that min-cut algorithm so that I can be happier about solving things non-manually. I think I did not write the graph theory longest path routine. I think Steve Forrest did, but he did it because I complained that we didn't have one, because one of the problems one year ended up being finding the longest path in a graph, which is the interesting problem, and actually harder than it seems. So the matrix plot is something I use a lot when visualizing these problems when I'm solving them, and I've added a bunch of Candy to it, like the sparse option, so that it's a lot more efficient when drawing big grids. The lots of things, lots of times when you want to turn an integer into, or you want to turn a string. So all your inputs from advent of code come in as a string, and you read them from a text file. And I mean, there's other ways to actually read things, but generally you have strings and you want to turn them, they might want to turn them into numbers, and it's a bad habit to use parse on strings that you downloaded from the internet. So I don't like to use parse. I prefer, so you can see that a lot of my worksheet actually has this at the top. It has a scanf. So this is a slightly safer way to take a string s and pull out and parse it into an integer rather than just dumping a mystery string into the parse command. And but no one wants to do this. So in Maple 2025, I actually added a convert target. So now you can just say convert string, comma, integer, and it does a safe parse into an integer. Anyway, and then inevitably, I run into bugs doing this because it ends up using weird corners of Maple, and so I file a lot of bugs, and then usually fix a bunch of bugs in January after getting frustrated and staying up all night um, uh, on problems. All right, so let's talk about some useful tricks that syntax candy in Maple gives you. So this is a trick. I'm going to show you the problem on from last year on day 4. Everything's a grid in Maple, or in I would say like a third of the problems in advent of code end up being mazes or word search grids or heat maps or things given as ASCII grids, and you want to put them into a matrix and you want to do something on them. And one of the problems when you're searching a grid, say, is the corner cases in the corners or the edges. I guess literally the edge cases and corner cases. And in that code, when you write those, like if you're walking across the grid, looking at all the neighbors, if I'm at grid point 1, and I want to look at all my neighbors, I just want to like look at position +1, position -1 in all the directions. And I don't want to have to write a clamp or check if my ranges are out of bounds. So I'm actually just going to make an array in Maple with some negative indexes, and that goes from, so if I'm looking from my position and I'm searching 3 spots in any direction, which I'm going to be doing for this problem, I just make the array 3 spaces bigger in each direction and fill it with empty stuff. So let's look at this problem. So the problem is that there's a story here. You meet an elf. The elf has a word search, and you are helping her solve her word search. So her word search looks like this. And what she's searching for is the word Xmas. These are all Christmas themed. She's looking for every occurrence of the word Xmas in the grid. So the easiest way to do this is put all these letters into a grid, and then search in every direction until you can find the Xmas's. And like I said, this ends up being, all right, let's see, this is day 4 part. Here we go. So here's the sample input from that one, and you can see that I have this, I parse it into a grid, and then I store it into a grid that, so I take the original input, I store it in OGrid. I see how big it is, and then I create a bigger grid that's padded out with empty strings and embed the original grid inside of it. So now that gives me the original word search and then a bunch of stuff on the outside. So now everything is really easy. I just walk along the bounds of the original grid, M and N, and at every spot, I look in every direction and I form a string. So here I cat sequence of the grid. So now here you can see that I'm referencing the grid, stepping in k times in each direction. So k goes 0 to 3 here. So I'm taking from the current position, I'm taking a string of length 4 in every direction. So now I don't have to do any special handling on those corners, which is great if you're trying to do this fast and you're trying to do it without bugs. Because when those corner cases and those edge cases are inevitably where everything like messes up and you can't figure out how to solve it. So this is like the most amazing feature of arrays. Because you can just embed you get these default cases, and then so here you can see I just if I'm at the edge, if I'm at 1 1, then I everything that's off the grid just shows up as blanks. So this test is going to fail, and which is fine. That's what I want it to do. I want it to fail quickly. Anyway, so that's a cool trick that you have available in Maple. It makes your life very easy. And all right, so let's all right, yeah, okay. So that's a useful trick. So then sometimes Maple has, I think actually I wrote a blog post about this on Maple Primes, so you may have seen this particular problem before. So a lot of problems, especially once you get to the middle of the puzzle challenge, they end up actually being mathematical problems. And if you're able to identify that and use Maple to do it, it can be very advantageous. So let's pull up day 13 last year. So here there's a whole story. You have some claw machines. So your claw machines are defined in a list like this. The claw machines have really ridiculous buttons. So each button moves a certain number of steps in the X and Y direction. So you have button A and button B. Here the moves 95 steps and X and Y. And what you want to see is, that the prize is at another location, and you want to know, can you press A and B in some number of times to get to the prize. So if you look at this is you want to take this many X, this many Y, and this many X and this many Y, and you want to, an unknown number of presses of A plus an unknown number of presses of B is equal to this. So this is a linear equation. It's two linear equations. So you actually want, this is going to be A times 95 plus B times 22 equals 8,400, and then A plus 34, or A times 34 plus B times 67 equals 5. So you have two simultaneous equations, and they need to have positive, or rather non-negative integer solutions. So you look at this problem and you're like, I have Maple. So like that ends up being like the hardest part of this, ends up being parsing the problem. So in this case, let's pull this out. We got I'm actually a great trick is that we have all these like C style parsing things. So you have so you can actually use scanf. So occasionally you get very structured text like this, and scanf ends up being your friend. Um, so here we have our 4 machines, and then you can actually you see that every machine. Let's get a Maple prompt here. So our machines, I'm doing the sample input it's just a list of 6 entries. So I have my coefficients, my left hand side coefficients, my right hand side coefficients, and so you can actually just plug this into fsolve, or sorry, into isolve. So you have that first integer equation, the second integer equation, and then you can check if there's a solution. And it's like, and you do it, and it just works. And so you try the sample, and then you go back, you load the actual input, which I'm gonna not display this. You see there's 320 machines, but 320 integer equations is not bad. So so this is one of those cases where uh, I got the answer very quickly, and quicker than most people in traditional programming languages, because you can immediately identify the problem as solving an integer linear system, and you can immediately say, my friend Maple has that in isolve. And actually linear algebra could do this for you too. It can actually solve them as rationals, and then you just need to check to make sure the solutions are integers, which is not hard at all. So I mean, there's some other things here, but the main thing comes down to that. And then, so part 2, so Eric Watzel is a cruel, cruel person, and he tries to anticipate how you're going to solve part 1. And some days he's kind, and his part 2 will be very easy. But some days he anticipates how you're going to solve part 1 in many programming languages. And he specifically formulates a part 2 to confound that. So here you can see that he anticipated that people would use linear algebra solvers in languages that probably convert all linear algebra problems into floating point numbers. So he gave you a big number, and then added that to the coordinates of the prizes, specifically to create numerical error when actually solving these. Because you could solve these, right? You plug these into SciPy, not SciPy, what's the other one? NumPy. And you just have NumPy solve all these using whatever its default solver is, and then you take the answer and you check whether the answer is an integer to however many decimal places. But when you start adding big numbers like this in, now it's harder to check whether your answers are actually integers anymore, because the numbers of the precision doesn't even give you the integer answers to the right number of decimal places anymore. So you have to do something different anyway, but not us, because we're using Maple, and isolve does not have that problem, and isolve just solves this just fine. So this is like one of those cases where you got like, there's a huge win for Maple. Maple's not as fast as C sometimes. Like the problem we saw that day 1, we wrote the stupidest thing that was n squared, and then we wrote the next stupidest thing that was n cubed. And some days going from n squared to n cubed goes from a computation that runs in a couple minutes in Maple to a computation that's going to take all day to run in Maple. And so then you have to reformulate your problem. But sometimes someone using C, they went from a nanosecond to 10 minutes. And so everyone kind of like, the problems are cleverly done so that everyone gets an advantage on different days. So I actually wrote a blog post about this particular problem on Maple Primes, and I encourage you to go check it out, because I actually talk about how there's hidden structure in a lot of these problems, and so the wrong solution will often get you the answer. So in particular, none of these problems had were what is none of these problems were zero, positive dimensional, so there weren't an infinite number of solutions and you didn't have to find the smallest solution. So if in the iSolve case, if there had been, if any of these had been under constrained, that's the word I'm looking for. If any of them had been under constrained, then you'd have to do something else and have to do optimization to get the smallest solution. But this was only a day 13 problem, and so that it didn't, there was enough difficulty for other programming languages that we didn't have that problem. But yeah, I discuss how you might solve it in full generality and how you might get around numerical problems in a blog post on Maple Primes. Anyway, so that's another reason I do Advent of Code, because it gives me interesting things to write about on Maple Primes, and the marketing department likes it when I write blog posts that are interesting on Maple Primes. All right, so so I have a bunch of ways that we're cheating at Advent of Code using Maple. So here's day 23 from last year. So this particular case, you're looking for an elf who is at a LAN party, and all you have is a map of all the computers connected at the LAN party. And so this suggests you're going to do graph theory. And if you actually look at the problem, you're looking for connections inside that graph. So in this particular case, part one actually is looking for all the 3 clicks inside the graph. So and you're actually looking for all the 3 clicks where the names of the nodes, or where at least the name of at least one of the nodes starts with a T. So Maple makes this not terrible. Let's see. So we have like our large graph here. It's easy to just pull those in. We're gonna I use the split command to split this into every line into the entry of a list. I use string tools words. So words is like split, except it takes out everything that's not an alphanumeral and then breaks those up into another list. So I get a nested list here. This ends up being pairs of node names. So then those are actually the edges of a graph. So I just plug those into graph theory graph here. I get the list of every unique machine with the vertices command on that graph. Actually, this should be quick to run. Let me just do this on the sample input. I need to get my keyboard back. All right. So yeah, Maple has been punishing me for using Linux because at least my desktop doesn't always get its focus back. So so sometimes I'll be trying to type into Maple and it's not working. So I haven't been able to fix that yet. So all right. So anyway, so now I have this, like you can see, it turned into a graph. It had 16 vertices, 32 edges. Actually, I just want to look at the edges, or I want to look at the vertices that have a T, that start with a T. So then I go through each of those, and actually I'm looking for 3 clicks. So really I can, but since I'm only looking at the specific nodes, I can just look at the neighbors inside the graph of each of those nodes and see if there are at least 3. So that's what I'm going to do here. And it's easy to find them. So that's part 1 of that problem. Part 2 of that problem, though, is actually there's too many of those. There's actually a lot in the original input. So actually, what you're going to look for is the largest set of computers that are all connected. So what you're looking for is the maximum click. And Maple has this command, find click, and find click actually finds the maximal click, but it'll also find clicks of various sizes. So if I wanted to find a click of size 3, I could ask it to find a click of size 3. Weirdly, it gives me node names in that case instead of or node numbers instead of names. So that's but what it doesn't do is it doesn't find all of the 3 clicks. So I did get a cheat on the second. I got a Maple cheat on the second part because I have a maximum click command that works very quickly on this case. It's a hard problem in general, but this is a tractable size. And then so that solves it easily. But then that gave me immediately a feature request that I logged to Jira. That's let's get a find all clicks command because there's a known algorithm and it's not so hard to do. But all right. So anyway, that's a cool problem. It helps a lot to know Maple's graph theory package and to know kind of what the universe of easily solvable graph problems there are when you're doing problems like this, because when you can reach for a graph theory command to do it all for you, that's always great, because when you have to write your own click finder, you're gonna mess it up. And I mean, okay, I'm gonna mess it up, and I'm gonna have an off by 1 error that I'm chasing for an hour at 1 o'clock in the morning when I should be wrapping Christmas presents. And so we try to avoid that. Makes my family happy. They get presents for Christmas. All right, so here's a problem from 2 years ago. I actually did this problem in the airport while waiting for a plane. Our plane was at like 9. It was taking off at 10 o'clock. The problem came out at 9 o'clock, and so I was trying to solve it on my laptop before we boarded the plane. So I was hopeful that it might be an easy problem because it was a Monday. So this is weird. It's a weird, there's always a weird story. So here you're in the jungle. There's a bunch of monkeys. The monkeys are yelling weird things. So there's so you want to find out what the monkey named Root is going to yell. And if you look you have a description of what the monkeys are going to do. So the monkey named Root is going to yell whatever the monkey named PPPW yelled, and add that value to whatever the monkey named SJMN yelled. And the monkeys that have constants are yelling those constants, but the other monkeys are waiting for the constant monkeys to yell. And then anyway, so this is an expression tree. And anyone who does symbolic computation looks at this and they smile because they're like, this is an expression tree. I just need to write all these as equations and then substitute them into each other till I get a constant. And that's what Root is going to yell. And I mean, there's a whole bunch of other things here that are explaining what's going on, but we probably have ignored everything here and are already programming it, which but then before you submit your answer, you always need to go back because inevitably there's a convoluted problem. But actually here, it's not. It's just actually what is the number that comes out of root. So let's see what we did. So this is, let's do the sample problem. Nice and small. The input looks like this. Don't read the real input. All right, here we go. So then there's 15 monkeys. I'm actually going to just put them all into a table. And I'm just going to actually just run a loop and do substitutions until the answer comes out. It's extremely fast. It's actually extremely fast, even if we use the real input, which has got almost 3,000 monkeys. It's about the right number of monkeys. So you can see that that's big. So I did okay. I got like in the top 2,000 on that. Lots of people have clever ways to parse syntax trees. But then part 2 of this problem is that, oh no, your instructions are wrong. That one of the monkeys on the list is actually named human, and that's you. And you have to guess what value you need to say in order to make the root monkey. So the root monkey shouldn't have said value 1 plus value 2. It should say value 1 equal value 2. So you as the human have to choose a number x so that this equation is true. So now that's a lot harder, but actually what I'm going to do is I'm just going to take I'm going to take that root node, instead of making it a plus, I'm going to turn it into an equal sign. I'm going to take the node that the monkey named human, and I'm going to turn it into a symbol. And then I'm just going to run that same simplification. And now the root node is a very simple linear equation, which I will solve. And that is the answer to the equation. So then you get the puzzle answer, and then I think that was the 150th person to solve this problem, which made me very excited, but also sad because being in the top 100 has a lot of cachet, and I was so close. But yeah, like this is one of those days where it's a gift to have symbols and to have them on the top level, because like, yeah, if you have SciPy, or if you have, sorry, SymPy, or you can create a symbol and make this happen. But it's not like change two things and do exactly the same thing in the first part, but now you have a symbolic equation that you can easily just solve. So yeah, Maple is a gift on this day. Excuse me. So yeah, it's not really cheating. You can use whatever you want, but some days it feels like cheating. All right. Here's another day where it's kind of cheating to have symbolic computation. This is a slightly harder problem to describe. This is from 2 years ago. So here you have you have inputs that are a bunch of seeds, and then you have every seed number maps to a soil number, every soil number maps to a fertilizer number, every fertilizer number maps to a water number, and so on until you get to a location number. And every one of these series of numbers is a piecewise linear transformation. So this every triple here describes a sort of a way to make a piecewise linear thing. So that, let's see, day 5 piecewise. So I'm not going to do this on this is extremely slow on the real input, but oh, I lost my keyboard again. All right, so let's import our friend string tools, because it's useful. That's my input. I'm gonna parse it. So you can see here my next favorite string tools command, which comes up a lot on these kind of inputs. So you can see like I have blocks of things that are kind of in different formats, and they're always separated by a full line break. So if I first use string split on 2 line breaks, that splits each of these things into a separate string. And then I can go through and parse each of them separately. In this case, they're kind of symmetric, so actually I'm going to parse them with split afterwards. But and maybe it's actually even interesting to see what this looks like. So you can see that first doing a string split on 2 line breaks splits each of these things, and then we're able to split them into lines again. So and then I have to do different things on different parts. So seeds, for example, has got its own thing, but like seed soil map has 2 map components and so on. So all right, so let's do that. Let's so the top line is just the seed descriptions, and the bottom line are maps that tell me. And it doesn't really matter what the maps are called. All we care about is these strings of numbers. And so these strings of numbers are all going to turn into piecewise functions. And the problem that you're asked to do is take these seed numbers and apply all of these maps and then find the minimum value that comes out. So, and you can actually see what these maps look like. So they're like, the first one, you can see that it's maybe not exactly what you think it's going to be, partly because we've done a convert piecewise to make it a little bit more normal. But it says if the X is out of range, it just returns itself. And then otherwise it has a transformation done to it. So that's kind of encoded in here. And then you just do this transformation for each one of these, each of the inputs. So then that's relatively straightforward, but it's made like super simple to formulate if you write it in terms of piecewise functions. So actually, if you look right here, I have this that's the functional composition. So I actually just take the functional composition of these 7 piecewise functions, and then I map that over the seeds. So I apply the composition of all 7 piecewise functions to each of those seed numbers, and then I just want the minimum of those. So it's a very simple thing to do. But then part 2 changes it up. So instead of just applying piecewise functions, now you actually those seed inputs are now changed from individual seeds to descriptions of ranges of seeds. So now you have a collection of ranges, and you want to find the minimum value achieved by that composition of piecewise functions over each of those ranges. So that's annoying, but you can formulate it in Maple by, let's actually, it turns out minimize doesn't like getting a big, doesn't like getting a big a piecewise function, a big nested piecewise function. So what I did here was I went through and composed them one at a time, and at each step I flattened them into a single piecewise function. So I think this one is maybe not so big that it doesn't show up on the screen. So here's the seed map, and now you have this map. and it's now this thing is very easy to minimize over. The actual input is here, I can show it to you. So this was that little map. It's just the actual input that you're given by advent of code is much, much bigger numbers with many, many, many more branches. So the actual piecewise numbers that come, or the actual piecewise functions that come up in the real input are a lot bigger, and it doesn't quite feel as magical anymore because these things are huge, and you end up running into some inefficiencies in minimize and piecewise functions that go on the list, and someday we'll make piecewise functions a lot more efficient, but you actually can solve it that way, which it's nice to be able to solve it in a in the sort of turn it into a mathematical problem and solve it as a mathematical problem. And I'm kind of cheating here by like some of these problems, it's late at night in December, and I have a messy worksheet that has nested loops and all sorts of crazy things. And then I solve the problem, I get the right answer, and then I'm like, oh, I should have done that with piecewise functions. So you can see that this worksheet is called Day 5 PW because this is after I already solved it in a really disgusting way. That I realized I could do it with piecewise functions, and so I built this very clean, elegant piecewise function worksheet to do it. All right, so Maple, the rich, like huge library of mathematical functions in Maple, usually helps you. Okay, it often helps you, but sometimes it throws you off on the wrong track, and you are and that sends you for a loop, and you're up till 3 o'clock in the morning beating your head against the kitchen table. And that happened to me here on in 2 years ago on day 23. I see Jurgen suggests I use piecewise tools flatten, and I will do that as soon as this workshop is over because it might actually work better. But it actually might be what is called by the anyway, that's a good suggestion, Jurgen. Thank you. Anyway, so day 23. So this is that day that inspired me to ask for the longest path command, and we didn't have one at the time. So this is I've written a blog post about mazes in advent of code as well, because so many things are mazes. So here you have, and they're always pretty to look at. So here we have an ASCII maze. It's mostly long, empty paths, but then there's some directional arrows. So these are slopes, and so that what that tells me is that you're going to go from a start to an end, and the fact that there's a directional arrow at every intersection means this is going to turn into a directed graph. So, and then, so yeah, you have it's a directed graph, but then you read further, and they actually you want to find the longest hike you can take. And in this case, it doesn't have to, and you actually, well, okay, and it says never step on the same tile twice. So that's good to know. So you can't take the same edge in the graph twice. So that's great. It's directed. There's no, we can draw it. There are, oops, it looks like this. I actually wrote where's, there we go. So this is, it's a directed graph. It's actually a weighted directed graph. So each one of these numbers counts the number of spaces you walk to get from intersection to intersection. Oh wait, this one's not the directed one. I actually wrote a terrible graph compression. There's a clever way to start with a maze that big, and you can iteratively compress it down to get rid of the straightaways. Because like the first time you make this, if you start with this graph, or if you start this with this maze as a grid, oh, sorry, I'm just going to scroll back and forth a whole bunch. You start at the maze as a grid. This is a node. This is a node. This is a node. Then you remove the walls, and then, but you actually don't need a node for each one of these things. So you want to compress it down so that you go from here to here to here to here, so that you have just the connections you want. Anyway, so regardless, if you start there, I'm sorry, I'm gonna scroll back. I did this in not a great way, but I did it with a custom Dijkstra algorithm that I wrote myself to sort of compress. You don't really need Dijkstra, but then ultimately, where am I? You have, wait, where's, oops, maybe I have the wrong worksheet open for this one. Oh yeah, this is my part 2 worksheet. Can I grab my, oh yeah, here's my part 1. So actually, so I actually use Dijkstra, my Dijkstra helper function here to compress that maze down into a relatively small graph. Where is it? Right here. And that, but in this case, in the first part, it's a directed graph. And then you can get the longest path if it's directed and it has no cycles by taking all the edge weights and just making them negative, or finding the maximum edge weight and subtract them, and subtract every weight from that. So now you're then the shortest path turns into the longest path, if you do that right. And so you can use the Bellman-Ford algorithm to do that. It works with negative weights, and it just works. But the problem is that the second part of the problem took away all the directions and gave you an undirected graph, and now asked for the longest path problem that doesn't revisit any edge or node. And at this point, it's late at night, and you have no idea what to do. And you're like, all of Maple sits before you. So I like had the crazy idea of like, oh, well, what is the longest path? And like, oh, maybe it's the one that visits every node. And it can't retrace any steps. So that feels like a traveling salesman problem. So let's use the super fast Concord traveling sales problem solver. And I used that. It worked. It got me an answer, although there's a bug in it, which has since been fixed, which caused me to stay up an hour later than it would have otherwise. But and we did that. I tried that, and I'm like, and it's not the right answer. And it's one of those things where now I've got the wrong answer in my head, and I'm fixated on. It's like, well, why is the traveling salesman problem not? Why isn't the traveling salesman solution not the right solution? And it turns out that you're not required to visit the all of the intersections. You're just required to find the longest path. And it turned out that visiting this node in the maze caused you to detour away from the most expensive paths. And so since you can't retrace any path, if you have to visit every path, that will constrain how you travel, so that you might have to go a sort of a shorter route by to visit every intersection. So eventually I had I realized that I was like I had gotten myself in a corner. I like everything looked like a nail because I had the hammer of traveling salesman. But instead of like backing up and just writing a depth first search, which would have solved this problem very straightforwardly, I doubled down on it. I'm like, well, let's actually do a traveling salesman problem on this graph with let's remove each node one at a time and do a traveling salesman problem on that to find a traveling salesman solution that visits every node but one. And ultimately, that found the solution. It's a stupid way to do the problem, enabled by the fact that there's a very powerful, fast traveling salesman's solver in Maple. Uh, but it's definitely a case of applying a jackhammer to a problem that needs a tack hammer. Um, so it's a problem that you're not going to have in C because, I mean, it might be because you could actually get bindings for the Concord library and and have ran down that path too. But if you have a language with fewer tools, you feel you aren't always going to fall into those traps. So it's like Maple giveth and Maple taketh away. So there's a little of both. So here's a advent of code is fun because I mean, it's fun regardless, but there's a lot of continuity from year to year. Eric Watzel uses some of the same themes. So there's always a maze. There's almost always a cellular automata. There's almost always something that looks like it's going to involve the Chinese remainder theorem and that doesn't. The In this case, there's almost always a scanners and beacons problem where you're given scanners with various coordinates that detect beacons at different coordinates, and you have to resolve the overlap of all the scanners and all the beacons. So, and then you can draw cool diagrams of that. So here's a scanners that have that scan according to a Manhattan metric, and they have detected some beacons, but there's a beacon that isn't detected by any scanner, and you have to find its coordinates. So I'll just show you the problem. It looks like you get inputs that look like this. You have a scanner at this XY coordinate, and it finds the closest beacon at this coordinate, and the actual input is of course much bigger and has like 10-digit numbers. And so you're looking for gaps in the scan pattern of these things. So let me pull up that solution, which is kind of fun. Wait, no, this is day. Oh, there it is. This is the one out of order. So again, this is another one of those cases where scanf is really nice. You can immediately pull apart the sort of plain text solutions into lists. So if you are old school and use scanf, it makes your life easier on these ones. All right, so then there's a bunch of parsing here, but this is solving the first part. And the second part is to find the gap in the scanners. So, oh wait, I should just run this. Why is that mouse blinking there? It's weird. All right, so this is the actual input. There's a whole bunch of scanners here. The first one just asks you to look at a single line of a single line of the input and count, or a single row of this thing and count how many squares have been covered by scanners, which is relatively straightforward. but it's one of these cases where he's asked you to pick a row and count the number of integer points that have been covered by the collective set of scanners. And then the next part of the problem is to look at the red square and find the one spot in the red square that is not covered by a scanner. And so this is one of those cases where Eric Watzel is evil, because he's given you a very easy problem for the first half that is a tool that will solve the second half. So if you can search one row to find how many things are covered, then obviously you can iterate from row 0 to row, is it 4 million? And you can go from 1 to 4 million or 0 to 4 million and just check every row and find the row that has a spot uncovered. And so you've already written the program that checks the row. So why shouldn't you make a loop that goes from 0 to 4 million and just does it on each row? And the answer is it's very slow. But like, one of the things that you get used to doing in Advent of Code is like, you make a copy of your worksheet. You write that thing that takes 2 seconds to write, but it's going to take an hour to run, and you set it running. And then you go to the other copy of the worksheet and start working on a more clever solution. In this case, I was not as fast as the brute force algorithm in coming up with a clever solution, but I should have been, because actually, if you take a moment and you draw the problem, you can actually see, well, if there's something uncovered, it's got to be at an intersection. It's got to be near the intersections of the sides of these diamonds. So you could use say the computational geometry package to look at line intersections. So you take all the segments in this collection, put there's a beautiful command in computational geometry that is that takes an arrangement of line segments and computes all their intersections. And then you take then you can just take the x coordinates, or the y coordinates of the intersections, and only look at those spots. So now that takes this problem from checking 4 million lines to checking 1,000 lines, and then it's super fast. But you can also there's also an even smarter way to do this, which is, if you look at this, so this scanner is you have an equation for what this is. And so what you want is, you want to find an XY point that is outside of the range of this scanner. And it needs to be outside the range of this scanner and the range of this scanner. So let's just solve that. So let's take an XY that's outside the range of the scanner S. So here, this is so this is this MH distance, the Manhattan distance of each scan line. So you want a scanner, or you want the scanner to detect a beacon that's farther away than the beacon in the description. So let's go back to that description. It said the closest beacon is this far away. So for each sensor, you want to find a beacon that is farther away than that one. So that's what we do here. So that's the Manhattan distance to the closest beacon. And so we have an unknown beacon that's we want the Manhattan distance of that unknown beacon from the scanner to be greater than the closest one. And we're going to do that for every scanner. And we're going to, we're going to assume that's a non-negative integer, and that it's less than 4 million. And I'm going to solve this with with a SAT solver. So Maple has the SMT lib. I always get T and M mixed up, which is SAT solver. It's extremely fast. It's so you can't use iSolve here because iSolve doesn't support inequalities. We should probably, it's like, that's on my to-do list. Like have iSolve call into SMT-lib in cases where there's inequalities. Of course, it's what the satisfy is not solve, right? Satisfy gives you a witness point. So it shows, so in this case, I know from the problem description that there's one solution. So satisfy is going to find me one solution, and that's great because I know there's one already, right? I know there's only one. So that's part of why we don't have this in iSolve, is that iSolve sort of expects, or users of iSolve expect to get all the solutions, whereas satisfy only gives you one. But maybe it's worth expanding that functionality. It's hard to say. This is really like actually solving this problem is more like doing CADs over the integers. So, or no, quantifier elimination over the integers. So it's a more complicated problem. Anyway, so that's a fun problem, and that kind of thing comes up a lot. And generally, yeah, you'll get weird metrics, or you'll get the non-continuous metrics to make problems not fit into standard libraries, so that they're harder to solve. So like this one, it's like it's actually got the Manhattan distance obscures it, right? But this is absolute value is in these equations. So you have to know how to formulate all that for whatever solver you have. All right, so let's I have 5 minutes left. Let's I'm not going to dig into this problem. This was a super fun problem though. You basically had infinite Tetris. You had infinite Tetris blocks coming down into a well, and you're asked, the first part asks you to find out how deep the well gets after 2,000 days, or 2,000 pieces drop. And then which you can just simulate. You can just simulate 2,000 pieces dropping and count the number, and it's fine. But then part 2 asks you to do it for 100 million pieces. And now like you can't simulate that anymore because it's too many. But instantly, any like veteran of advent of code, and I wasn't when I did this one in 2022, should know that the only way you can solve that problem is if there's some sort of cyclic behavior. So there's going to be a tail of non-cyclic behavior, and then at some point you're going to fall into a cycle. So you have to write an efficient enough simulation so you can simulate far enough to detect a cycle, and then you do modular arithmetic to solve the answer for the gigantic number. So I'm not going to get into the solution of kind of running out of time. Instead, I just want to show you a bunch of pretty pictures. So when the problems are relatively easy, I try to draw beautiful pictures. So this was a problem that ended up turning into finding intersections of lines and finding the frequencies of intersections. So I drew a bunch of plots with to make those pretty intersections. This was back in 2021 before we had Maple Prime's art gallery. So these not all these pictures are on those. This was a super fun problem in 2021. you're given a series of points and then descriptions of how to fold the points over and over again. And so you kept folding them. So each like frame of this animation, every time the color changes, you do a fold. And eventually, after you've done all the folds, a series of ASCII art, if you're drawing it on a terminal, but a pixelated letters appear, and that string of pixelated letters is the solution to the problem. And that's extremely delightful when you get it right and you see it emerge on your screen. And it's and then so I was able to make this. I made this animation again. This is with sparse matrix plots from grids. All right. There's a lot of like just maze chasing where you're simulating the movement of something in a maze. So this is again sparse matrix plots of sort of frame by frame of a guard moving through a museum where he turns, I believe, clockwise every time he hits an obstacle. And the actual problem here was much bigger, it's a much bigger grid, and came down to find a spot where you can put a new obstacle so that the guard falls into an infinite cycle, and which was a fun problem. A little extra hard for a day 6, I think, but day 10 was actually just you had I'm going to show this to you because it's kind of interesting. You're given a grid that's that's a maze, but you're given it as with these F's and J's and pipes. So you're given an ASCII description of a maze, but it actually looks like this. So some of these things are connected and some of them are not, and you have to decode that into a boundary fence. And then in this case, you have to count the number of integer points inside this curve. So this was like, I made an animation of this. Although in this case, there's, I think it's Pick's theorem that actually gives you a really easy solution to this problem. So you don't actually have to go through and do all the geometry. And I learned about Pick's theorem after spending 3 hours solving this problem. So it's always fun to solve the problem and then go look at the internet forums. They're on Reddit to see how other people have solved it in clever ways. Oops, and is that really the end of my slides? That is the end of my slides. So I guess I was supposed to have conclusions there. So in conclusion, so I would invite you all to come participate in Advent of Code this year and use Maple. I plan this year. So this year it's a lot more approachable as in the 11th year of the since it's the 11th year of the code or the puzzles. Eric has found that it has consumed his life, and so he needs to simplify the contest a little bit so it doesn't take up so much time for him personally, and he's gotten rid of the pesky global leaderboard now that everyone just uses Claude or Gemini to generate code to solve the problems. And so now you're really competing against people you know on private leaderboards. And so this year it's only 12 days. It's going to go from December 1st to December 12th. I'm going to set up a private leaderboard for people doing Maple solutions, and I'll do daily threads on Maple primes for people to participate in the advent of code problems, and we can discuss. We're gonna have a comment thread where we discuss how we solved it in Maple, and talk about best solutions, and everyone who wants to join the leaderboard, we can compete to see who can solve them the fastest. And if and we can even set rules so that we're competing all in the same time zone if people want to do that. I'll post about this on Maple Press.